It's my pleasure to introduce Nikolay, who will tell us about Cherednik algebras via Coulomb branches.
Thank you very much. Okay, so yeah, again, I'm sorry that I have to do this by broadcasting my screen. So the only way I can talk right now. But yeah, I'm very happy to be here and to talk about Cherednik algebras. So I will just begin by stating what the goal is. It's to describe explicitly the Coulomb branch algebra which we called RGN, or maybe the cohomology, equivariant cohomology of RGN, for the case that G is a complex reductive group, and the matter or the finite dimensional G representation is just the adjoint. Okay, so let's begin by sort of recalling the setup with Coulomb branches. So this I'll call Coulomb branches from algebra. And I'll sort of recall what Junho introduced for us, and then later what Sonia said last week. So again, the setup is G is a reductive algebraic group, or the complex numbers. And then I'm going to use interchangeably the notation G sub O to be positive loops into G. So this is matrices with Laurent polynomial coefficients. And then also the full loop group, G sub K, will be with the field of formal Laurent series coefficients. And then N is going to be just a finite dimensional representation. And then likewise, we can extend scalars. So N sub O will be the tensor product of N with formal Laurent series, and N sub K with the field of. And I'll use Z for the power series. Okay, and then let's recall the definition of the Coulomb branch. So this was the space of triples RGN. So it consists of G comma phi, where G is in the loop group. Phi is a section of the trivial bundle over the disk. And the compatibility is that G phi is also an NO. And then so this is a variety, and then we associated an algebra called the Coulomb branch algebra by taking equivariant Borel-Moore homology of this space RGN. And I will always work with Borel-Moore homology, so I'm going to suppress the notation Borel-Moore. And here, the C star action comes from the loop rotation. So it acts on the variable Z mapping to H bar Z. And we can rewrite this.
Should you mention down by actual GO and by then actual GO?
I take the GO equivariant homology instead of.
No, right. No, there are two actions which are one on the left and another in.
Okay, yeah, okay, so great, thank you. Yeah, I'm gonna then write it as the class of G comma phi where you mod out by the geo action on the right. Thank you. Yeah, and now there's a way to rewrite this algebra sort of in a more symmetric way in which the convolution product becomes clear. So we write it as NO mod GO, fiber with itself, over NK mod GK. And it's this latter description which we'll actually use to sort of really write down elements inside this algebra. Okay. Now, just this definition alone, it's hard to really see what it looks like. And then this, there's this idea by Ben Webster to sort of enlarge, like make a larger framework for which the Coulomb branch just sits inside as an endomorphism algebra. And this was explained last week by Sonia, so I'll just quickly recall the setup. So may write explicit elements of this Coulomb branch by sort of enlarging here's what I mean. So let I denote the Iwakouri subgroup. So this is the pre-image of the Borel under the evaluation map from GO to G. And it's called the standard Iwakouri. So let's define this category B. Or telegraphic B, consisting of objects being pairs of parahoric and lattice So recall parahoric means it contains a conjugate of the Iwakouri. And U will be a p-invariant lattice inside NK. Now, what are morphisms of this object? Well, we may write it in the following way. So given a pair of parahoric lattice, and then another parahoric and another lattice, this going to be defined as the C star equivariant homology of sort of a space like so. All right. Now, of course, this definition is set up so that the Coulomb branch algebra is precisely the endomorphism of the pair NO-GO. So GO is the parahoric and NO is the lattice. And this, okay. Now, this definition allows us to do several things. First of all, we can introduce sort of a larger Coulomb branch, which will be called the Iwakouri Coulomb branch. So this will be denoted by taking endomorphisms of, instead of taking the pair Hort to be GO, we just take it to be I. So that, and then we still take NO as the lattice. So the effect of passing from GO to I is essentially saying, instead of taking GO equivariance on the left and the right of Argand, you take Iohori equivariance with respect to the left and the right. So you mod out by I on both sides. And sort of in all of these Hecke algebra, we have seen, and like the finite case, and then the affine case, and then the double affine, which we'll see today. The difference between these two is that the Coulomb branch should be thought of as the spherical counterpart of this larger Iohori Hecke algebra. And so here's this fact. These algebras are Morita equivalent. And in fact, so here's a claim made by Webster in his notes, which I think is, well, I'm a little surprised. It says that, in fact, the Iohori Hecke algebra is a matrix algebra over the spherical, and it's of rank size of the boundary. So I'll put a question mark here because I know that this is the case in a lot of cases. But I thought maybe I'll put a question mark here and ask like if anyone. No, we don't use this fact at all. If anyone like has seen this, or I haven't seen in this great generality before. But yeah, like it certainly holds in the cases that we will encounter, but it's kind of surprising that it always holds. I thought you would need some sort of assumptions.
You say a bit about composition.
Composition?
In this case.
Yeah, I mean, everything is going to be done canonically using the convolution product. You see, like, if you have P prime, U prime, and then P double prime, U double prime, you'll write another diagram like this, where you have 2 primes, 1 prime, and then when you take the fiber products, so it's like you just collapse the ones with the primes, like it's just standard way convolution works. Yeah, thank you for the question. Yeah, so everything here is like done using convolution products. Okay, so yeah, okay, so I think we just introduced a category for which the Coulomb branch sits inside as an endomorphism algebra. The advantage here is that we can actually write down many morphisms inside this category. And in fact, these will generate the like endomorphism algebra. So let's write down a few important. So I'll call this, there's going to be 5, and I'll start the list from 0. First is multiplication by a class in the equivariant homology of a point. Here, T is the Lie algebra of the torus. So yeah, maybe I should say in the beginning, T will be a fixed maximal torus. And the I equivariant homology is the same as the T equivariant homology because sort of the unipotent radical contribution, so Iwahori is unipotent semi-direct torus. The unipotent part is affine, so you can collapse. Like homology is insensitive to affine. So this is the fact is you multiply by polynomials. Now the first sort of non-trivial one is that you can change the pair of works. So given a pair of works, one sitting inside the other, and a lattice U, which is stable under the larger pair of work, we can push forward and pull back along the diagonal inclusions. So this will be morphism from PU to QU, given by sort of pushing forward along this diagonal. So this defines a cohomology class, or a homology class. And then to pull back, we'll be sort of pulling back along a section of this. Oh, sort of call it the opposite back. Next, we can also sort of swap two lattices. So given pair of lattices, U and U prime, which are p-invariant, there's this morphism denoted by R, and this will be sort of the class defined by this inclusion. And this R will act on, I will define a polynomial representation later. It'll act on the polynomial representation by the Euler class of these two lattices. So we call that briefly in a bit. Next is given any element of the extended affine vowel group. So you can write this in two ways. It's finite vowel group semi-direct with the co-character lattice, or it's also just the normalizer of the loop group, the torus inside the loop group, or the torus. Then there's this Y morphism, which is just the graph. So the vowel group acts on the pair of work by conjugation, and it acts on the lattice by translation. So this plays the role of P prime and P prime. Okay, and
sorry, in one, so in first morphism, so you're describing some homology class in this
yeah, yes.
And this is push forward. So delta push forward of what? Of fundamental class?
Yes. Yes.
And pull back of what does delta do?
Well, I think delta up is just a projection.
Yeah. And you pull back.
Yeah, you pull back, yes.
You pull back and so what's the homology class in the product? We pull back from the input.
I want to say fundamental calculus, I'm not entirely sure.
Okay, well, yeah.
Let me get back to you, yeah.
Yeah.
Yeah, yeah, I was hoping you wouldn't ask me this, but yes, sorry, I'll get back to you. Yeah.
Sorry. Yeah, what are these delta?
Those are the diagonal, so high lower star is like well, I want to call it, this is what Ben Webster's used for his notation. He calls it the opposite diagonal. I'm not sure why it's called opposite. And you sort of reverse the arrows and use the other inclusion. Okay, and there's this last sort of morphism is you just compose pull back and push forward so that you actually get to endomorphism. So for each simple reflection, let Pi be the parabolic corresponding to the simple root. Then given a lattice stable under this parabolic, we define this endomorphism psi I given by push-pull. So this will be an element of our Ewell-Horry Coulomb branch. And in fact, yeah, this has a name, it's called like the Mazur operator. Yeah, and let me just for completeness sort of recall, yeah, because I actually didn't know what the minimal parabolic is. So here, Pi is the minimal parabolic inside the Lie algebra plus this subalgebra for any finite reflection. And then sort of for the affine reflection, 0, you take this. And here theta is the longest or the highest root, which sort of equals h bar minus alpha 0. And g sub theta is like the white space of that. So these are the simple parabolics.
Sorry, Leo.
Thank you. Yeah, sorry. Okay. And yeah, just final comment. So we wrote sort of 5 different morphisms in this category. They do in fact generate all the morphisms. I believe last week this category was called the it was called the Steinberg algebra. We sort of take the direct sum over all such pairs. And yes, it is possible to write down all relations amongst these by common theme, looking at a faithful polynomial representation. Here it'll be called the GKLO representation. So that's all I had to say for So the recollections of the Coulomb branch. And now we'll completely shift gears and talk purely about algebra. Yeah, so it's a great place for questions so far.
Still be anything, but it's I, right? Not you.
Here,
Yeah.
thank you. Yeah, I mean, you're absolutely correct. So since I wrote over here, I do want I, but of course you can make sense of these for any lattice.
Okay.
Yeah. Okay. Okay, so let's know. Yeah, so the goal, remind you, the goal is to describe this endomorphism algebra in the case of the adjoint. Now, I'll tell you what this algebra is algebraically. And then, so section 3 will be showing that these two sections are actually isomorphic. Okay, so the setup is, as before, T inside G, maximal torus. And then I'll try my best to write this Gothic T to, yeah, look like that. And then lambda will be the co-character lattice. And inside lambda, we have the co-root lattice. And then we can associate two affine vowel groups. One is denoted WF. So this is the semi-direct product of the finite with the co-root. And this is a Coxeter group, so it's generated by simple reflections. And then we have this larger affine vowel group called the extended affine vowel group. This in general is not a Coxeter group. There's these additional length 0 elements, which are a little tricky to deal with. If you like, if you wish, you can do what I do, just assume the group is simply connected, so that these two are then the same. So there's, yeah, so the proof will always sort of, every proof you see will be the Coxeter case, and then you treat the length 0 elements separately. Okay. Now let's define the key object. So this is called the degenerate double affine Hecke algebra. And sometimes in the literature, it's also called the trigonometric. So this HG is a quotient of this free algebra generated by the group algebra of the extended affine vowel group and the polynomial algebra in the torus. And I'm going to extend scalars and write down H bar kappa. So these are deformation parameters. And my notation, it's just, I invented this notation. I'm sorry if it's not standard. So this will mean you take polynomial algebra in the torus, but the coefficients are allowed to be polynomial in H bar and kappa. Sort of, and extend scalars. So it's a quotient of this semi-direct product modulo the relations that simple reflections act by this kappa twisted way. So when kappa is 0, this contribution dies. Oh, sorry. And it's the ordinary Weyl group action on polynomials. So you're twisting the action on polynomials. And then the length 0, and so again, you always have to treat these separately, will just act in the standard way. Okay, now you may wonder, where does this h bar parameter live? Well, this comes again from the Weyl group action on the torus. So observe, so note W acts on the polynomial algebra with just an h bar parameter via the following way. So we take W and W, a co-weight or a co-character, mu, and sort of a degree 1 polynomial alpha, then Wx on alpha the standard way. But it's this affine contribution. So this co-character mu acts on alpha by an h bar shift translation. And then the parameters are sort of fixed under the action. So this generates the action on degree 1, and then you sort of induce. Now, there's you can enlarge this action to account for this kappa deformation as well. So there's going to be this kappa twisted. So this is sort of, oops, part 1, 2. In fact, may upgrade to an action of the full degenerate Daha on the polynomial algebra via, so yeah, so the extended affine Weyl group acts the following way. It acts exactly as it should if you read the relations. So this is how W hat acts, and then the polynomial part of HG acts by multiplication by polynomials.
Sorry, so you describe action of W hat on C H bar of C, and so it's a finite Weyl group, and then there is a co-weight lattice.
Yes.
Mu is any element.
Yes. Yes.
Yeah. Okay.
Yeah, I just wanted to sort of emphasize this H bar appears because the mu acts by translation, right? H bar. Yeah.
It's a basic question, but you speak on like the length of elements of affine, extended affine module.
Like how to define the length?
Yeah.
Well, for the affine part, it's fine, like it's just a Coxeter group, and then you define length as you do in the finite case, like you just have this additional simple root S0, like the affine root, declare that has length 1, and then you sort of pick a minimal, like given any element of WF, you can write it as a unique, or sort of as a minimal product of simple reflections, and the number such is declared that way.
Maybe instead I should ask what are the length 0 elements? Is there a nice description?
Yeah, there's a nice description. It's a bit technical, and yeah, maybe just if you assume the group is simply connected, you don't have to worry about this at all, and so nothing will be lost. The length 0 part, like the number of such, is just equal to the quotient of co-character by co-root, so it's just some finite group. Like there's only, yeah. So like,
Thank you.
yeah.
Here, SI can be like this. SI are all simple reflections.
Yes, including that one, yes.
And how does FI reflection have on F?
Okay, so for SL2, so there's no length 0, so there's only WF, so this is generated by S0, S1, and it's just two simple reflections, and then S0 times S1x by translation. Then you have alpha 1 is alpha, then alpha 0 is h bar minus alpha, where the torus is just spanned by this root. Then S1, so I'm describing how W hat, sitting inside here, acts on this polynomial algebra. So S1 acts, so it's going to be a polynomial in alpha with parameters h bar and kappa. So this, just reading off this formula. So first you act on alpha, so S1 just reflects alpha. And then you do the kappa twist. So this will be minus alpha h bar kappa. Alpha. Now you ask, how does S0 act? So S0 sort of acts by reflection on alpha 0, and you can write it in the following. So it sends alpha to minus alpha plus 2h bar. So if you I was hoping to skip this step, but it's good that you asked. If you look at the notes, I will skip as a reminder to myself. Yeah, okay, now, so the proof, yeah, the proof of 2, like the fact that this trig Dalhat X.
Sorry, we probably asked too many questions.
No.
We didn't try it. Polynomial second polynomials. Yeah.
Oh, yeah, I was present. So that, of course, geometrically corresponds to my important morphism number 0, multiplication by a class of the equivariant homology of points. Just you act by multiplying. Yeah, it's important, but yeah, good question. So proof of 2, again, the strategy is you just assume. Yeah, so W affine is Coxeter. So it's generated by simple roots or simple reflections. And then suffices to check action respects the sort of braid relations. Yeah, so I mean, this is really straightforward. For instance, let's check that SI squared acts by 1. So this is the formula for the action. Now, if you hit this once more by SI, the first part will be just F. And then the second part, well, this is invariant by SI. Because SI acts on the numerator and denominator by -1. So SI squared acts by 1. Then you just have to check the braid relations. And this also follows just by direct computation. It's a pure computation on the vowel group. Okay, so a corollary. Well, I don't know if it's a corollary or a lemma, but sort of you can say that this polynomial representation is in fact just inducing the trivial rep. So this is, if you like, we can call this also the PBW theorem for the trig Daha. So as a vector space, Hg is generated by polynomials in the torus and extended vowel group. So it's saying here that only the polynomial part survives when you take the tensor product. And that's exactly what this is saying. And then, yeah, so Hgx here as I described over here, and then it also acts here naturally on the left. In fact, these are isomorphic. And this sort of idea, it appears everywhere, even in the very beginning where we look at nil Hecke algebras. So if in the finite case, we again exhibit such a phenomenon. Okay. So continuing on, so for any element of W hat, or maybe I'll say WF, let TW be TSI1, TSIK, where W is SI1, SIK, minimal representative. And the TSI act on the polynomial rep via dagger. So this is dagger. And sort of the PBW theorem is that if we fix a basis of the Lie algebra, then the operators, so polynomials in the x's, and then the TW, are linearly independent. As operators on the polynomial algebra. So as a byproduct, this action that we just defined of the trig Daha is faithful. Now, the proof of this is very straightforward. Again, I'm just going to assume for simplicity Okay, so now you can observe that the operator given by simple reflection, so this SI, you can rewrite it where you just capture the part acted on by SI, and then the part, you just extract the SI coefficient and the constant coefficient, and then it looks like the following. Notice this coefficient is never zero. That's the only thing we use. So then TW is just going to be like a lower triangular invertible matrix. W T prime such that FWW is non-zero. And that's the proof.
So T is here like T on the right is no, but can you install maybe it can't be true because
This?
yeah no, sorry, you're writing TSI as a sum of SI and 1.
A linear combination of those,
So
yes.
multiply its action of the while group element. Not, I mean, T means twisted group, twisted action by coupler, but on the right you're writing it as untwisted action.
No, so this equality is of operators acting on the polynomial algebra.
Yeah.
Yeah, and here it's just reading from here. You say
Yeah.
I just extract. Okay, so the SI coefficient here, it's 1 plus
Yeah.
cap over alpha.
Yeah, it's true.
Yeah.
It just should it should be something else on the right, not CW prime. I think so. Because you are
Oh, yeah. It's just W prime. I'm so sorry. Now I understand what you're saying. Yeah. I'm so sorry. Yeah. Yeah, that's important. Yeah, thank you very much. Yeah, but the important part is that it's the highest element is non-zero, it's invertible, so the change of basis matrix is invertible. So it's linear. Okay. Okay, so doing good on time. As a corollary, HG is, as I mentioned verbally, is the tensor product. So, and if you like, you can call this a triangular decomposition. So you see you have polynomials in the torus, the vowel group, and then polynomials in the group torus. So this is the algebra torus, this is the capital T check. Yeah. And this is as vector spaces, not as objects. And yeah, now let's introduce an important element. So this is called the symmetrizing or primitive idempotent. So let E be the average of all elements of the finite vowel group. Then we also call sort of EHGE will be called the spherical degenerate or trig double affine Hecke algebra. So little d will be for degenerate. Now let's try to write down the basis of this now. So we have a basis of the big algebra. Now let's write a basis of the smaller subalgebra. So HG times E on the right. Well, what we do is, so we can swap C lambda and CW. So just put CW on the right-hand side. And then when you do CW dot E, E is symmetric. So W acting on E is just E. So as a vector space, you can rewrite this the following way. I'll just stop writing TensorFlow. So you just, by hitting E on the right, you kill the vowel group. And now, multiplying by E on the left is the same thing as symmetrizing this on the left, which is the same thing as symmetrizing the big algebra with respect to the conjugation action of the vector. So let's now write what this does element-wise. So given an X tensor lambda inside HG, symmetrizing by the W lambda, so like the stabilizer lambda yields another element X tilde tensor lambda, where now X tilde is like W lambda invariant. And again, anytime I introduce a kappa in the polynomial rep, I'm using the kappa twisted W action. So that's the only way the vowel can act. So thus, we may as well assume X itself is symmetric under W lambda, and then symmetrizing further. Now, so we just have to add over all elements of the coset lattice. We find E times X tensor lambda E is the sum over all cosets W X tilde W inverse times W lambda times E. And here lambda was any co-character. In this symmetric sum, we can just pick the one for which W lambda is dominant. So we may assume lambda is dominant. So now we've obtained a large list of elements of the spherical degenerate Daha, and in fact, these are a basis of it. Yes,
I think it was in this was W sub lambda.
it's the stabilizer of lambda. So it fixes lambda. So the spherical subalgebra has a basis given by these expressions. So it's possible to write down elements, but writing relations down is not possible. So if that's the cost you pay by passing to some smaller algebra. By the way, this is frequently, or at least in the rational case, this is commutative. I think it might be in this case as well. But this is, no, it's not. So this is smaller algebra. You have these list of basis elements, but you cannot write down relations of it. in a way that you could for the larger algebra. Recall sort of the full Daha itself just had very simple relations, but you cannot write down such relations with the spherical algebra. Great, and I'll conclude this section by the following. So a remark. We may assign a grading on the Daha by declaring W hat and the parameters of degree 0, and the polynomial algebra has degree 2. Then the associated graded of the trigonometric Daha is just algebra. So you take the group algebra of the finite-dimensional group, semi-direct, the polynomial algebra T. So this now acts in the ordinary way. There's no H bar, there's no kappa deformation. So it's the ordinary semi-direct product, and then you take like just H bar and kappa as variables separately. And then likewise, the spherical subalgebra is just going to be the W invariance. And now I'm going to write it in this following clever way. Which is very suggestive. So I'm going to take the cotangent bundle of T check, TV. So this is TV times the Lie algebra of T. That's because the extended affine vowel group can be written as finite vowel group times co-characterized, and the co-characterized is just the polynomials in TV. And again, the reason why you pick up the W invariance is because you symmetrize. See, sort of multiplying by E on both sides just means you symmetrize. You pass through the symmetric invariance. Okay, so that concludes the purely algebraic part. Are there any questions? Yeah, let's take a 5-minute break just so I can walk around. Resume in like 5:06, 5:07.
Someone left I don't know if I can see, but I don't know.
So these T's are in the double or the double.
Ready? Okay, great. Let's now discuss the proof of the main theorem. The theorem, there is an isomorphism of algebras going from the degenerate or the trig Daha to this Iwo-Hori Coulomb branch algebra. For the pair G comma N being G comma adjoint. And I'm going to denote this Iwo-Hori Coulomb branch by calligraphic A superscript IW. And here the lattice we take is the Lie algebra of the Ewald. And this isomorphism is actually explicit, determined by generators. It's given by Si plus 1 maps to R of Pi I, psi I, R of I, Pi. And then W goes to the graph. The parameters sort of are fixed. And the polynomial part maps to the equivariant, the T equivariant homology of a point. And let me make a sort of a brief detour remark about how these parameters actually appear, because it is very sort of subtle. There's actually two sorts of deformations going on. So the H bar deformation is given by the loop, the C star. Yeah, it's given by loop rotation on GK. So C star acts on the loop algebra by sending Z to H bar Z. Now, this kappa, this acts on the matter. It acts on the representation N. So I have to give you a C star action on G, and this is given by embedding the principal SL2 subalgebra inside G. So it's given by the C star action. In other words, the gradient is given by the so-called Kazan gradient. And this is called scaling. Action on G coming from C star mapping to SL2 mapping to G. And this is the principal SL2 term.
Large.
Huh?
Groups. Sister, sorry. It's should be either C or with firstly.
Yeah.
Ah.
Yeah. Yeah, and then the it's called the Kazan gradient, like this embedding.
And how does it differ from the kind of naive action where you just scale everything in G with weight 1?
Oh, is it that?
I don't know, but that's definitely one action you could take that would commute with the adjoint.
Yeah,
So
okay.
maybe it's the wrong one to take.
I actually spent quite a bit of time looking this up. It was hard to find references. So I thought it was Kazan gradient, but I'm not certain.
It also it should be an element of algebra, and it's not quite clear what. I mean, H is is element of H C star.
Oh, yeah, right. I think it can't possibly factor through the inclusion of anything into G, right? Because it has to, I think, shouldn't it have to commute with the action of G? And if G's semi-simple, right, then
Well, okay, I'm gonna write down Kazan gradient with a question mark, but I think it is Kazan. I'll get back to this. Yeah, sorry, yeah. Okay, yeah, and furthermore, yeah, so just continue. So furthermore, this isomorphism restricts to one on the spherical subalgebras. I'll put this in a box. And now I do have like a serious question that I want to ask Gus or somebody. So it seems that there's actually two notions of an Ewell-Horry Coulomb branch algebra. So in this specific case where the matter is Ewell-Horry Lie algebra, we get this object, and it's well defined, and it's the correct one as stated in this theorem. Like this is a correct theorem as stated. But if you look back, the way Ben Webster introduced Ewell-Horry is by taking I and then n sub O. For us, n is G. This seems like it's a different Ewell-Horry Coulomb branch. It is possible, sort of, when you take, yeah, I think a priori it's different. And then on the other hand, like in general, like when you have just a pair G comma n, I think this is the only reasonable Ewell-Horry analog of Coulomb branch you can consider. Do you have any comments, anyone?
It's a good question. Yes, so the difference is in the matter. Is in the in the lattice, N of O or Lie of the Ewell-Horry. Yeah, and I comma N of O. Right.
Yeah. Yeah, sort of. It's unclear to whether these are the same in this special case or not. Like, I think this is the more reasonable, in general, notion of an Ewell-Horry Coulomb branch, but the one which gives you the degenerate Daha is this one. Anyway.
And if you use N of O, you should get something like naively a little bit bigger, right?
Right.
But probably just by a
Anyway, we don't use this red text, but I just wanted to point out that there are like competing notions of Ewell-Horry analog. Okay, so here's a proof of this main theorem. The proof, if you have read Chris Ginsburg, where they discuss the finite, like Neil Hecker case, is literally the same. In fact, I gave a talk on this at the Bunchy seminar this quarter. So the strategy is to use the faithful polynomial rep and show the same image. So we've already discussed the first embedding, and I don't know what it's called in the trigonometric case. In the rational case, I know it's called like Dunkel optum. So I'm going to write that down here as well. But yeah, it's the polynomial rep we discussed in section 2. And in the first one, it's called the GKLO, which I will briefly give an overview of right now. So the GKLO rep comes part of like this larger framework, which Webster works with in this category B. So given a pair of objects UP and U prime P prime, so it's lattice paraphoric. Convolution gives us a map as follows. And now for us, we take U and U prime to both be the lattice, so stereophoric. Which I denote by this calligraphic I, and P, the paraphoric, are both I, which you can factor as following. Yeah, and given this product, we can then write the Lie algebra as torus direct some affine space. And then what this means is, well, we can compute this equivariant homology of U mod P in the following way. So this is, so U is calligraphic I, P is straight I. Now, homology is insensitive to affine spaces. So we can, from above, kill Lie U, U tilde. So it'll be H of torus, and then from below, so point mod U tilde is also contractible, so it'll be just T. Again, now for some reason, the Lie algebra T is affine, so this is just point mod T. And this is just the polynomial representation that we saw before. And yeah, if you want to introduce a kappa, we also just introduce another C star action, which comes from this, I want to say Kajdan grading. But yeah, there's an additional C star. You can add another C star here, and then you'll get the kappa here as well. So yeah, that's how the polynomial rep we saw in section 2 arises geometrically from convolution product. Okay. So now let's identify their images. So we have to show. So now all it remains to do is to show both sides act on the same way on the polynomial rep. That will show that their images agree. So let's compute this action. So H G as a module over the polynomial ring is, so to the PPW theorem, generated by the simple reflections and W of length 0. And if W with length 0, then YW with the graph satisfies. So this is a general relation which holds in this convolution algebra. And this is exactly the relation appearing in the degenerate Daha. So we're happy. So this is just a sketch. And now for the non-zero length, the simple reflections, let's compute. So we have to compute what this does. I'm going to copy and paste. Okay, so applying this operator on F, first, we have to deal with this R. So the R acts by Euler class. And the Euler class of Bi mod I, so this means you have to compute the weights of this paraphoric modulo horn. And the weights you will find computation are just minus alpha I plus kappa. So the first contribution is just multiplying by this scalar. Move this to the. Okay, now the psi I acts by Demazor. So recall this means F, or I'll use a different letter, G goes to GSI minus G over alpha I. So we can write this as RPI comma I. And then we just apply this to that polynomial, and we get alpha I S I. Okay, and finally, we have to act by the Euler class. But the Euler class of the other, or of this, well, this quotient itself is this, yeah, this quotient is 0. So the Euler class acts by 1. So nothing happens. And then I'm going to rewrite this as just F Si plus F plus kappa F Si minus F over alpha I. And this is precisely the result of applying Si plus 1 to F. This kappa twisted action on polynomials. Thus, the conclusion, we found that HG embeds into this evil hoary Coulomb branch algebra. So it's a graded algebra morphism. So here we're using that both actions are faithful. So both actions are faithful. And all elements of HG act the same way that their images under A act. So we obtain an embedding from HG into A IW. So a priori, we don't know that this is surjective. But we can conclude it is surjective in two ways. First is by citing like this meta theorem by Webster that these are the only generators of this endomorphism algebra. So this is surjective because this operator and the graph generate here, and this is due to Webster. Or you can just compute the graded dimension of both sides. So we know the graded dimension of HG because we have this PBW theorem. And then again, sort of, there's this computation you can do on the convolution algebra, which will presumably give like a computation for the dimension of the other side. Okay, so that concludes the first part. Now we have to argue.
Actually,
Yeah.
good question. So is there like a simple kind of formal way to see in Ben Webster's setup that the GKLO representation is faithful?
Yeah, I'm trying to remember how the proof. So I didn't. He didn't prove it in his like notes. So I'm citing the seminar notes he wrote for, like the MIT summer school.
Yeah.
He didn't give a proof there. I don't know where one can obtain a proof, but I imagine.
I think it. Yeah. Oh, I was just going to say that I think it should sort of follow from I forget whose talk it was in, maybe Alex's, where he proved that this iota star localization map is injective, and I think basically from that uh, basically that's the same construction of the same representation. But I wonder if Ben has some slick kind of way to do it more I seem to remember that in the original Chris Ginsberg he used that there's like an invariant form, right? And that but it's tricky to do that here because everything's sort of infinite dimensional.
Uh-huh.
Anyway.
Okay, I'll do my homework and return to you. Yeah. No, I couldn't find like the proof in the notes, and so it was hard to find a better reference. Yeah, maybe I'll just email him. Okay. So yeah, thank you for the question. Let's discuss the spherical case. So this will be done, and hopefully it's a familiar strategy. So again, we're going to construct sort of an embedding of algebras as follows. So let R inside HG map to R prime inside Yohori. And then we're going to, I'm going to spell this map out explicitly. And to do that, I have to introduce two operators. So one will be an X operator. So this will be given by the following. So we go from Iwahori, the algebra, to Iwahori positive loops, to loop group, positive loop group, and positive loop algebra. And then Y will be sort of going in the opposite direction. Okay, so these are operators in this category B defined by Webster. Now claim the map ERE goes to averaging of X R prime Y is well defined and defines the morphism that we desire. And again, the strategy will be the same. It suffices to show they act on same way on the polynomial algebra or polynomial graph But now, instead of taking the full polynomial rep, you have to symmetrize it. In other words, you take the symmetric invariance. Okay,
So just one second. I think E is just one second.
I'm sorry?
It acts only on one side. If you're hitting algebra with E on both sides,
Okay, yeah,
it's only on one side.
Yeah, okay, this is really bad notation. Okay, yeah. Okay, I'll just erase this entirely and just write down this. Okay. Yeah, you symmetrize the polynomial rep, which means you take the symmetric polynomial algebra. Yeah. Okay, so let's show this. So we need to interpret what's x and what y are. Well, x, it's well, y is easier. First, let's do y. Y is going to be a map from G0, G0 to I. Okay, well, the algebra associated to this is on, and on the Euler side, it's the full polynomial algebra. And I mean, there's only one embedding of algebras which you can consider, and this is, of course, just the standard inclusion. And this is no surprise, it's because pi upper star is given by pullback. So that is given by pullback, and then the Euler class here is again identity. Okay, now the other operator, the x operator, will be in the other direction, and again, there's kind of only one way you can write this down. If there are no h bar kappa deformation, and that namely that will be called the Reynolds operator, or like the averaging operator, and essentially that's the same case here. You just have to make sense of how to twist this by kappa. So let's compute. First, we have to understand what R does, and then what pi lower star. So R acts via Euler class. And now the weights of this action are going to be able to form alpha plus kappa for all negative roots alpha. For all alpha negative. And then pi lower star is like some sort of averaging. So combining, we get x since f to, I'm just rewriting the composition of these two operators. Okay. So what can this operator be? So I make the following claim. The operator x equals the Reynolds operator, namely So E, yeah, remember E is like you take 1 over size W of all the sum of all W. So why is this the case? Well, I'll only give you a very brief sketch.
Nikolay, sorry, should W be also applied in denominator, or like you're writing F goes to sum of W F over product of all this W? Since in our case, the denominator just have both similar.
Yeah, thanks. Yes. So yeah, let's check this in the, so the strategy is, if you've seen any proof using Reynolds operator, it's the exact same. So let's check in case kappa is 0. When kappa is 0, this contribution dies. And then you are, yeah, then you're just taking the sum, the alternating sum of the FWs. Wait. Well, okay, let me argue first. Yeah, I'm a bit doubtful. Yeah, let's just look at this. So kappa is 0, this is the product of alphas.
I think that the W shouldn't have been in the denominator, right? Because if there's no kappa, that will cancel the L of W, and then you'll get the actual Reynolds operator, right? Because length of W is a number of inversions, right? So the number of guys that get sent to there.
Yeah. Yeah, so yeah, if kappa is 0, then sort of the product of alphas here will be killed by the product of alphas here. And then you're just summing over all FW, and that's exactly what W dot E is. And then what you do next is show that this operator X sends symmetric F to identity. So it's identity on the symmetric polynomials. Which like agrees with what this claim is saying. And then you show that the X is invariant under the symmetric group. So if you, yeah, it's equivariant with respect to the symmetric group action, or the value group action. So that's the strategy, and that completes the proof of this claim. And just combining all, so yeah, I will try to go a little bit quicker now. So combining, we get the inclusion and here R equals R prime. And then we go to averaging. And this is just ERE restricted to the invariant polynomials. Okay, so we finished our claim that the first claim that ERE and XR prime Y over W act the same way on the symmetric polynomials. So this gives us our desired embedding. And again, we can conclude that this embedding is an isomorphism by computing graded dimension of both sides. So this is possible. So that completes the proof of the main theorem. And sort of, yeah, in the final, like, I'll go 5 minutes over, if that's okay. Okay, so I want to draw this cool chart. Actually, yeah, I want to draw this. No, I'll copy and paste the chart. Let's make it quicker. Now discuss it. No, not stay over too long. Section, I'll call this section Cherednik algebras. More general. So let's sort of orient ourselves. The following this. So specialize the case that the group is GLM. Now, we discussed this middle row here. So for our matter representation, we took the adjoint representation. We computed the Coulomb branch algebra is the spherical trigonometric or degenerate Daha. And then we consider this larger Uhori version, maybe I'll put like R tilde. This Uhori version of the Coulomb branch algebra, and this is the full trig Daha. And these algebras sort of were two parameter deformations of the following simpler algebras. So in the spherical case, we take functions on the cotangent bundle of T, and then Sn invariants. And then on the bigger algebra, we take functions on the cotangent bundle, tensor the group algebra. And these are indeed weighted equivalent. And sort of another way to obtain these algebras from associated graded is by just specializing H bar in kappa, to 0. Yeah, I mean, I said that they're not C star parameters. So this is a little, yeah, you just in the relations of the Daha, you specialize H bar in kappa to 0, and you get these algebras. Okay, but now there's this multiplicative, so one higher step in the hierarchy, analog of the degenerate Daha, and this is called the spherical, this is called the Daha itself. And this is obtained by just replacing homology by K-theory. So this is taking the K-theoretic Coulomb branch. Now, the parameters here will be Q and tau. And now you replace one copy of the Lie algebra by the torus T. So instead of taking TV times Lie algebra T, you take TV times T, the group. And again, so it's not here, when I say associated graded, it's not actually a graded algebra, but it still does make sense to like specialize to Q equals 1 and tau equals 1. And the way that the Q and tau parameters are related to the H bar and kappa parameters is by setting Q to exponential H bar and tau to exponential H bar kappa. And the way so there's a specialization map going from the Daha to the degenerate Daha, given by formally plugging in Q and tau, these parameters, and also plugging in the capital Y as exponential H bar little y. So you can go from above to the middle row by introducing this H bar kappa and then just taking the formal limit as H bar goes to 0. So you take this algebra, you complete at H bar, then mod out by H bar squared equals 0. So you only pick up the linear term. Okay, so that's going one step above, but you can also go one step below, in which you replace the group TV by the Lie algebra T dual. And this is called the rational Daha. So here you have to take a different matter representation. You take G plus this framing, so it's called like, then you take a standard rep. So the group acts on the Lie algebra G by adjoint and on Cn by the standard. Then you run the same calculation, this is done by Ben Webster. Exact same recipe, like you introduce this polynomial representation, you compute the generators in this algebra B, and you will find through a lot more work though, that the Coulomb branch algebra is the spherical rational Daha. And then the Iwahori version of it is the rational Daha. So these are also called like the rational Cherednik algebras. And here they have parameters h bar and c. Again, they're related by the same exponential way. And again, you can obtain the rational case by a formal degeneration procedure. Like any element in the group TV, you write it as exponential something in the Lie algebra T star. But this exponential has this h bar parameter, and you just take the limit as h bar goes to 0. And then you precisely pick up the relations in the rational Cherednik algebra. And yeah, it's just a neat way to package like all of these three types of algebras are called Dahas, or they're all called Cherednik algebras. So it's unfortunate that they all have the same name, but sort of I think more or sort of like a standard way to call it is you go from spherical Daha to spherical trigonometric, or also like spherical degenerate, to rationals. Like the rational is like a double degeneration. And now one question I wanted to ask to end the talk here is what happens if you start at the rational Daha and then take K theory? Like, Gus, do you know?
I was about to ask the same question.
So
Yeah.
my guess is it's the nil Daha, but I have no idea.
Well, I thought you could get nil Daha by at the K theory level just taking n to be the trivial representation.
So yeah, is that the nil? But is
Yeah,
that
exactly. It's Grassmann,
yeah, is that the single? So is there a difference between nil Daha and nil Aha?
I guess I don't know definition of nil Aha. But so for me, nil Daha algebraically would be what you get if you take the relations in the Daha, so like the top column, and then you clear out all the tau inverses. So you have stuff, with only tau, and then you set tau to 0. Or like more concretely, if you take the Macdonald operators, the algebra generated by multiplication by symmetric polynomials and Macdonald difference operators, and you set tau to be 0 in Macdonald difference operators.
I see. Yeah, I mean, it's certainly possible that different ends produce the same Coulomb branch. I honestly don't know what, yeah, like the question. Yeah, it copied down in my, yeah, well, what is this Coulomb branch? K-theory Coulomb branch.
I mean, it should be pretty straightforward to write down the difference operators there, right? Because you're just going to have like an extra factor in the numerator coming from that of the localization formula coming from the that extra copy of the standard representation. But like in terms of quivers, right? It would be like a quiver with a single loop and then like one square vertex, right? It'd be like C to the N pointing to C, but a square C and a loop on the C to the N. But yeah, it's interesting. I never knew about this bottom row of the table. It's really cool.
Well, okay, so I'm like 99% certain it's correct. The way it's formulated is actually a much greater generality. So I forget who the original authors were, but they consider they call it the sphere, like the cyclotomic rational Cherednik algebra. And for that, they took G plus Coulomb from CL to CM.
Uh-huh.
And then the effect is that then this group is replaced by gamma, which is Sm semi-direct Z mod Lz to the n. And I just took L equals 1. And I think I'm pretty certain that when you take L equals 1, then the spherical, then the cyclotomic rational Cherednik algebra just becomes the rational Cherednik algebra.
Uh-huh. I feel like that example in the middle row. Oh, and actually, now I'm really confused.
Well, the middle row is what we proved.
Yeah, right. It's probably good. Yeah. Um, and in the rational case, instead of representation by shift operators, right, it's representation by some different, like these Dunkel type operators, or
Sorry, what was the question?
oh, yeah, I was just trying to orient myself about how to think about the polynomial representation in the bottom row.
In
So,
the
so like,
rational case?
yeah, in the rational case, yeah. Uh-huh.
Yeah, then it's called the Dunkel operator. Like, I mean, in the case of SL2,
Yeah.
I think it's like H bar times. Wait, I wrote it down in my other, let me go, my other page.
But it involves some derivative, probably, right?
Oh gosh, I know I didn't write it down. Yeah, it involves some derivative. It's H
Uh-huh.
bar d by dx plus, and I'm going to forget
What
the
over
contribution. It's some bulk
SI
contribution
minus one or something, yeah.
with C. Yeah, like something inside.
Yeah. Uh-huh.
Yeah. Um.
Oh, yeah. I mean, it must just be like the first term in the Taylor expansion of the old operator at the next level, right?
Yes, that's right.
Oh, yeah. Uh-huh.
Since it's just a symbol keysbook,
Yeah.
that's algebras.
Yeah, I just don't remember the formula off the top of my head right now.
Yeah, so the second term should just be the same as the other one, right? And then the uh-huh. Yeah, that's a good question. And there's also probably some other insane row further up in the table where instead of taking K-theory, you take like elliptic cohomology.
Right.
But Cherednik does have some kind of like, what was it called? Double elliptic algebra or something like that?
Oh, I haven't heard of it. Interesting. Yeah, that's cool. Yeah, and I also, yeah, I know that Webster and co-authors, like I only discussed the GLM case, but I know that they, in general, like wrote down the Cherednik algebra as a Coulomb branch. But I don't know if anyone has looked at like the K theory of that. Yeah,
So the comparing K theory and equivariant homology or homology, like when do they differ and like when do you get the same thing?
I think you always get different thing. Yeah, I mean, I guess the only example that I keep in mind is like when you look at the T equivariant homology of a point, you get sort of polynomials in T. But when you look at the K theory of a point, you get polynomials in T. So these are not going to be invertible, right? Like if it's one dimensional, it's like polynomial algebra, and here you get Lorentz polynomials. So I don't think they'll ever be the same.
That's correct.
So the expectation, like you should expect like K here some multiplicative analog. The exponential. This. Oh, yeah, thank you.
More questions?
Thanks, Nikolay. That was great. Sorry I wasn't there in person, but
Oh,
yeah,
no,
great.
no problem. Yeah, thanks. I still got to grill you with questions, so it's all fine.
Cool. All right. See you guys.
Maybe if there are no questions, we'll take